Hello, Narnach here. Welcome back to the Human Resource Machine. Last episode, I spent a lot of time on the Fibonacci Visitor. Managed to get it down to a very fast runtime, but the problem was I was using too many instructions, and no matter how much I tried, I couldn't get it below the target. I think I actually had about half an hour of material that I cut out of the original recording just to make the video a bit nice and concise. And today I sat down to give it another shot, and within 5 minutes I had it. So a quick recap. The Fibonacci Visitor. We get numbers in the inbox. And for each of these numbers we have to generate a full Fibonacci sequence up to, but not including, the listed number. So in this case they already nicely hinted the Fibonacci sequence here. It's 1, 2, 1, 1, 2, 3, 5, 8, 13, 21, 24, 55, 89. So it starts with 1, 1, and after that the next number is the sum of the two previous ones. So 1 and 1 makes 2, 1 and 2 makes 3, 2 and 3 makes 5, 3 and 5 makes 8, and so forth. So I have gotten pretty good at optimizing it for runtime. But the thing is, I have 21 instructions in my shortest solution, and I needed to get down to 19. So let's recap the strategy we ended with last time. We have a 0 here. The Fibonacci sequence, it starts with 1, 1. So what I thought, well, let's bump it once to increase it to 1, and then we have a 1 that's permanently stored here, and then we can just add 1 to A, add 1 to B, and then we already have our initial values set to 1, and we don't have to increase them in place. So it's a speed increase, and actually it doesn't really matter if you do it inline or not. Speed-wise, it doesn't really matter. So after that, we take the number from the inbox, because this is our termination condition. Once we're done, we need to check the inbox before we start sending numbers out, otherwise we get an error. So we set that into the goal. Then we take the 1 value, we put it into A, we send it out, we copy it once again, we put it into B, and we send it out. And then we move on to the main loop, where we take a number from A, we add it to B, and we store it in temp. Then we send the number out, because that's, well, the Fibonacci, it's the A number plus the B number makes the next number, which we store, and then we have to replace the oldest number in the cycle. But in this case, if I would overwrite A, which is the oldest in this case, I would then have to, in the next cycle, have to replace B, which is not good, because then I basically need to have the loop run twice. So I needed a simple sorting mechanism in place. So that's why I store the sum in temp, because then I can take the value from B, overwrite A, take the value from temp, overwrite B, and that way they're shifted. And you can just ignore temp, because you always put something in, but you never manipulate it, so there's no need to clear that. So that's exactly what we do here. Let's see, and if at any point, oh yeah, and also before we do a check, so we store it in temp, and we subtract the goal. Or actually we read the goal and we subtracted the value from temp, so that if we know that the goal value minus the number is negative, that means we have exceeded our goal. That's a termination condition, so that's why we jump out, and then we just go back and we start all over again by resetting A and B to 1. And otherwise we do the shuffling sort thingamajiggy, and then we send the number out and we loop again. Okay, so that's a recap of last time. I went into a bit more details last time, since I actually wrote it out and thought it out as I was going. So, a couple of things that came to mind. What I'm doing here is I set up the number 1, and then I copy it to A, copy it to B, and I send it out. So I'm sending it out, I'm sending the value number multiple times out. And also because I'm sending it out, I'm doing extra things, because I need to read it again and so forth. You could say, well, if I have the number from 1, if I copied it, I write it to A, why not immediately just write it to B? Well, sure, That's fine. But you still need to send it out. And then you need to copy it once more and send it out to start with the sequence 1, 1. So numbers wise it doesn't really matter. That's my thinking, so that's why I organized it the way I did with this setup. So it was nice and logical. But one thing came to mind. Well, here I'm already shuffling numbers and sending stuff out. So what if the first 2 numbers are actually part of the main sequence? So if I can get even 2 instructions out of the setup code, then I can optimize the flow. And that's exactly what I did. So let's jump over to the solution I came up with. Exactly 19 instructions. So there's no more bump. This one stays 0. So what we do, we read the value, we store it in goal. Then we read 0, we copy it to A and B. Then we bump B in place, so we get a sequence with 0 and 1. And then because we bumped B, B is increased, but the number we're holding is also increased. And that was used to be a 0, it gets increased to 1. Or it's the number that B ends up with. So we can just immediately send that out. That's our first one is out. Then we still need to send out a second one as part of the sequence. But the nice thing is, this one was initialized to 0. This one is initialized to 1. If you add 0 and 1, that makes 1. So we can use the main sequence to generate the second of the ones. And that's exactly what I do here. I think this is actually just unchanged. It's only the setup that has been changed. And that's how you get to 19 instructions. So I'll run it. And this is, it's just Fibonacci. So I was so close yet so far, and the difference was just a slight different way of thinking about it. So that's problem 22 solved. And actually this is both 19 instructions and it's also 154 steps. So it even would meet the speed challenge thing. But accidentally already solved it with 97 steps in the previous episode. So we can continue with number 23, the littlest number. What's a littlest number? To reduce our carbon footprint, management is requesting the smallest numbers only. This is a public relations exercise. The results are going straight to the landfill. Yay! For each 0 terminated string in the inbox, send to the outbox only the smallest number you've seen in that string. Okay, you will never be given an empty string. Okay, that's also good, so we don't have to reset it to 0 and use that as a default. Reset and repeat for each string. What's a 0 terminated string? Go ask your boss on the previous floor. Okay, well, we've already done that. So there will be a sequence. So let's start. We read the inbox. And let's, for now, restore it. Okay. Yeah. That's always we start with a first number. Then we read it again. And let's say we also want to store that one, so we have a second one. So we call this one A. We call this B. Okay. So we have an A and we have a B. Well, we know how to check which one is larger. And that's by subtracting them from each other. So I'm thinking, let's say A is the smallest. So this is small. Let's rename it. Okay, then we recall this one to check. So that's the number we are checking, if it's smaller or not. Slightly getting better at drawing letters by hand with a mouse. Okay, so the reason we can put the first one into small is because it's the very first number. By definition, the first number we pick is the smallest we've seen so far. So that works out. Then after that, we have a loop. So this is the loop that we run to see if the number we pick up, the one we're checking, if it's smaller than that one. So this is the compare. Let's write down comp. Okay. So, how do we know if this one is smaller than the other one? And that's if we take this number and we subtract the previously smaller number. Let's say the previous number was 5 and the new one is 2. So if we take 2 and we subtract 5, it becomes a negative number. If that sum becomes, if it becomes a negative number, we know it's a smaller number. So the nice thing is, we stored it into check and we're still holding it. So what we can do is we can simply just subtract the previously smaller number. And if it's negative, we can actually, we jump out of the loop. Because then we know it's smaller, then we need to replace it. So then we have to reload the number because we're holding the difference in our hands. So we need to load it again. And we store it into the small. Okay. And after that we need to jump back. Yeah. Okay. Also, if the number we have is a 0, then we need to stop it. So after we take a number from the inbox, if it's 0, then we can actually just check. We jump out. Then we take a copy from the smallest number, we outbox it, and then we jump back to all the way to the beginning. Okay, so there's a lot of jumping. It's probably not efficient enough, but for now we got 14 instructions and it's a pretty straightforward implementation. So let's have a look if it's even working or if I missed something vitally important. Oof, oof, oof. Yeah. Okay, so that actually worked. We have a 0, so then that means that's done. Okay, so far so good. So let's see how it handles a new cycle. So we put it down, sure, boom. Next number, put it down. Okay, so we always override whatever came before. Okay, that means the cycle works. We have a working solution. That's always step 1, make it work. Next step, reduce instruction count and or make it faster. Okay, so we're pretty close. We need to cut out 1 instruction and to make it run slightly faster. It's only 9 instructions, or 9 steps. That's pretty good. So let's see what we do. We copy this, we go to the second tab, we paste it in. Most of the time, there's a lot of jumping going on. So if I can rearrange some of the jumping, so that there's, for example, the end condition. In the end, we jump all the way back to the beginning. Before we do that, here, we jump down. So if instead what we do is we jump to the top, then we do a copy from small and the outbox, and then we just have a jump that skips this. So this is a one of the default setups. We start with a jump into the main loop. And at some point, if we have a termination condition, we just jump out so we can fall through. So it saves us 1 jump in the loop, which is gonna save instructions. Thing is though, we still use 14 instructions and we needed 13. So this is probably gonna save us a little bit of speed. We were 84, maybe it's gonna jump down to 80. But we still need to get 1 instruction out. So let's see what else we got. So we have the value, then we subtract it, which is efficient because we no longer have to pick up a number, that's good. Then we have a jump if negative. Okay, that's so interesting because there's a jump back. Is there a way where we can, if there was a natural jump somewhere, we could use that. For example, this is a natural jump. You always need to jump if it's negative. You need a jump to close the loop. But there's no natural point in between, for example, that we could use to eliminate this jump. Or could we? Actually, from a runtime perspective, probably we can. So after this we jump back. So if we make this a jump that just skips these instructions, we just put these in, put those in. So yeah, because we've read the inbox and we stored too small, so this is the very start, and we skip this. And then the negative should go over there. Okay, so that's some rearranging of the loops. We still are one instruction too many, but for the runtime, this might just get us there. And it's just some creative rearranging of the loops. Because we're only gonna go into the flow once, but we are repeating multiple times. So if you rearrange your jumps to account for that, it might help. So we went from 84 to 80. That's it saves us 4, but it's not radical enough. So let's do another copy. We do a paste. Okay. So let's go through it one more time from the beginning. We start with a jump over the exit condition. That's copy the small number and sending it out. Immediately afterwards we check the inbox. So if we come in the first time, first thing we do is pick up a number from the inbox, we store it in the small. Then actually we never actually store anything in comp, so let's clear that. That's less confusing this way. So all we do is compare things that we're holding in our hands. Okay, so we jump in, we read it. Okay, next thing we do is another jump. Boom. Okay. Because this is our let's copy things back. The number is indeed smaller instructions. So we skip that. Then we get over here. We can even just do it like that. Doesn't really matter. Just keep it clean this way. Alright, so next thing we do, we pick up a number from the inbox. Then if that number is 0, then we need to exit. Yes, that makes sense, because that's our exit condition. We always check it the moment we pick up the inbox, because then the number we're holding is useless and we need to stop. So if in that case what we do is we take the number from small. Since we're still holding 0 in our hands, we need to pick up the small number and we send it out. There is nothing really we can do about that, so that makes sense. Okay, so if we didn't pick up a number, we picked up another number. So we store it into check. Then we subtract a small number. Actually, I think we could get rid of the copy. I think we can get rid of the copy. Because we're holding the difference. So in this case, let's throw it away. So we're holding the number that we picked up, that we're checking. We subtract the small. If it's negative, that means we need to restore it. So rather than copying from check, what we can do is we can just add the small number again. Let's again exercise with numbers. So the small number that's stored is 5. The number we pick up is 2. So we're holding 2 in our hands. There's 5 on the floor. We take 5 off. 2 minus 5 is negative 3. That's a negative number, so it's smaller. So then what we do again is the 5 on the floor, we add it to the negative 3 and we have 2 again. And then we can just store that. So that's exactly what we're doing here. We add the small number and we copy it back. So we override it, which also means we no longer need this. All we need is a place to remember the small number, and that's all we ever need. And after we do that, we fall back into our main loop, so to say. And the nice thing is we got our instruction count down to 13. And also what we did is we took one instruction out of our main loop, because we no longer store the number. If we have 5 sequences, or at least more than 5 inputs, that might actually get us there. So let's run through. I don't think I made a mistake in the implementation, so it should just run through. And we'll see how fast it is. Ta-da! Got it. So, size 13, that's an exact match, and we actually managed to get it down to 71, from 80 to 71, so that's 9 steps faster by taking one instruction out of the main loop. So, we solved number 22, the Fibonacci Visitor, and we also did a perfect implementation of the littlest number in one go. So I say that's a very good episode. Next time, mod module. But that's gonna be next episode. So I thank you very much for watching. If you haven't done so already, consider subscribing so you know exactly when the next episode airs or when one of the episodes in my other series airs. You might like them. And with that, I thank you very much for watching and I'll see you again next time.